So in my experiments with magnets and cubes, I wanted a way to actually quantify the force required to turn a cube. Hi friends, QBQ here. I hope this is going to be a really quick one. I've got 3 other cubing videos in edit, and I've realised that this video will be kind of useful for my later projects where I'm experimenting with magnets of various strengths and sizes in different cubes. So this video is kind of important for me to get out first. Incidentally, if you're interested, the 3 videos are a DIY 3D printed cube with no mechanical core, that's just magnetic.
Hello darkness, my old friend.
Another video is me magnetising a cheap cube, and I've got some really good tips for that. And the 3rd video is about me upgrading this beast of a cube by GAN, the GAN X IPG. I wanted stronger magnets than they supplied, so I've upgraded that. Anyway, subscribe if you want to see those videos, click the bell to get notified. Right, let's get on with this. So in my experiments with magnets and cubes, I wanted a way to actually quantify the force required to turn a cube. Because often you have to rely on a YouTuber to say, oh, this feels buttery or clicky or grabby. It's difficult to actually quantify how it feels. Feelings are very subjective. Some people like super strong magnetic cubes. I'm one of those people. Usually, as the manufacturers make them, they're not quite strong enough for me. I like a very loose cube, like this, but with super strong magnets. And GAN, for instance, even with the yellow inserts, it wasn't strong enough for me. So I would be very interested in knowing the actual force required to turn cubes with certain magnetic arrangements. Really, I want to be able to compare different cubes or the same cube before and after I modify it somehow. I thought it'd be lovely to actually get some figures on these things rather than just kind of guessing, oh, this one. And in order to do that, we need to do some experiments. Now, I looked up the force of turning things, and apparently it's torque. I'm not an expert or an engineer. I'm just a kind of a enthusiastic DIY maker type person. As far as I can feel, the range difference between a non-magnetic cube, I mean, that's probably just hardly any force whatsoever, and a super strong magnetic cube, it's not a lot of difference. I mean, we're talking quite low numbers here. So a device to do that commercially would be expensive, I think. I looked up small value torque meters and they were extremely expensive. So I think I've come up with a much simpler and cheaper solution. It's a little bit Heath Robinson. Essentially, it's a seesaw with a square cup. It's got some foam inside. It's 3D printed. It's in 2 parts. You've got a labelled graduated arm on each side so that they balance each other out. Every centimetre you've got a number. Then you'd hang various weights off the arms at various intervals until it turns. That was probably a bad example because that's very slight. Let's go with this one. It's got a reasonably strong magnet. You get some weights. These are actually just British coins. I've weighed them, so they're very accurate. This one is 10 grams, including the little copper hook. This one is 20, 50 grams, 100 grams. So you hang it over the edge, making sure that the front can actually turn. If you have it like this, obviously it won't turn. And then you hang some weights. So let's try 50 in 6 centimeters. This number 6 is 6 centimeters from this point here, the axis of rotation. 50 grams at 6, it's still holding. 7, 8, 9, so it went at 10. I think we have to measure the force at which it just doesn't turn, which is essentially the force at which if you go above, it will turn. Oh, it's just there. So at 10 centimeters, 50 grams barely holds. So we could put another 10 grams, look. So I think basically that there is the torque required to turn this cube. So I'm going to do that on various sides. I'm not going to do it all on the same side in case a couple of the magnets aren't put in there properly. I'm also going to do it on every single cube I've got here. Also going to measure what the cube is like at 45 degrees, like this, which is essentially with no magnets, because none of the magnets line up. That'd be interesting to know the kind of torque required to turn the cube if it had no magnets in. This one on the 45-degree angle with no magnets, 10 grams doesn't do it. 20 easily does it there. There we go. So I would suggest that would be the figure. 20 grams at 10 centimeters. So I'm going to collect all the data and we'll see what it looks like. Okay, so here are the results. Firstly, apologies for the hand-drawn graph. I think first off we should discuss this axis here. This is the force required to turn the cube. Down here is not much force, and up here is lots of force. The unit I've decided to use is the gram centimetre. Now that's a slightly unusual unit of force. Usually torque or twisting force is measured in Newton meters. But gram centimetres and Newton meters are essentially the same thing, on the surface of the Earth that is, apart from the size of the numbers you use, the scale. For our purposes, gram centimetres has a better size of number. It's more convenient for us to use, as we're measuring very small forces. Newton meters are better for high torque applications, like when you're talking about car engines, something powerful. Trying to compare these very small numbers is just painful, so for our range of forces here, gram centimetres are just easier to read and understand. Also, they're quite easy to visualise. For example, 500 gram centimetres is the twisting force you'd feel if you put a 500 gram weight on an arm that is 1 centimetre long. Or put another way, 250 grams on a 2 centimetre arm. Or 50 grams on a 10 centimetre arm. If you were holding the axle, they would all feel the same, because it is the same amount of force. Also, I should mention here, where you see a short bar, that means the force measured to turn the cube was the same on both faces I tested. I actually tested the white faces and blue faces of all the cubes, and where the bar is longer, like here, it means that one face was the upper force and the other face was the lower force. It's a simple way to show possible variations between faces on the same cube. It shows any inconsistencies nicely. And the little horizontal lines here, they're the force I measured while the layer was at 45 degrees. In other words, when the magnets weren't lining up. Anyway, having explained all that, let's have a look at the different cubes. The first thing I can say is there's definitely a good correlation between the forces I've measured in these cubes where you can adjust the magnets in them. In these cubes you can physically change the strength of the magnet or the position of the magnets. And when you put in some lines, this correlation is very obvious to see. And this is quite a good sign that this has some merit. For example, the GAN 356XS. This cube has a magnet you can't change the strength of, but you can change its position. If the magnets are moved to the outer setting, it's quite a lot more difficult to turn the cube. It requires more force, the magnets feel stronger. And as you move the magnets in towards the centre of the cube, it gets easier and easier to turn, as the magnets feel less strong. And actually this makes perfect sense, as they have less leverage the closer they are to the centre of the cube, so they should feel less strong. And the correlation is also good with these other cubes by GAN, the GAN X IPG numerical and the GAN X IPG version 5. Now in these two cubes you can change the strength of the magnets in them with different swappable inserts. GAN provides 4 different strengths of insert with each of these cubes. Now the inserts described as strongest, the clear ones, they show a much stronger force required to turn the cubes. They feel a lot stronger. And as you put in the weaker inserts, you certainly feel less and less strength from the magnets. Mean that these results are probably quite good and the experiment is valid, which is awesome. This means this might be a decent way to compare the feeling of magnets in different cubes, or compare the same cube before and after you modify it. Now there seems to be an anomaly here. I think that's a measurement error. Also it's weird that here, on these two GAN cubes, the lowest magnet strength, actually the inserts have no magnets in them, the force measured when turning the cubes was below the force measured at 45 degrees. I'm not sure what's going on there. Perhaps it could be a measurement error, or there's something else going on. It's a little weird. Looking at a graph like this with various cubes on it is really cool to compare them. You can see very clearly which cubes have very weak feeling magnets. They're the ones with the forces measured closest to the force measured at 45 degrees. It's as if the magnets don't really have much effect on the feeling of the cube. Now for me, I like this kind of force on my cubes, quite strong, just a bit above the maximum strength that GAN provides. So to satisfy me, I've created some DIY 3D printed inserts that are super strong. That'll be another video coming out soon. So if you want to see that one, click subscribe. Now here, this is the super secret area. As a side note, it's also worth noting, moving a magnet in towards the axis of the cube also has a different effect on the feel of the magnets. Not only does it make the force required to turn the cube smaller, they feel less strong, the magnets can be felt in a larger portion of the turn, the closer they are to the axis, as the magnet's apparent size in degrees over the turn increases. So you see the strength going down as you move them towards the axis, as we saw in the GAN 356XS, but there's definitely a secondary effect where the range of the arc in which you feel the magnet increases too. So you feel them weakly but over a larger arc of the turn. If the magnets are on the outside, they feel strong and distinct, and if they're closer to the axis, they feel less strong but can be felt over a larger arc. So they're less distinct. So in summary, this seems to be a really cheap and reasonably accurate way to measure a cube's reluctance to turn, the force required to turn it, both with and without magnets. I'm actually really surprised how good it is. The next step I'd like to take is to try and make a digital version of this. I've already ordered a small Arduino and 2 very small load cells that might be just right for this. This would mean it would be quicker to measure these things and potentially much more accurate too. You'll have to wait for an update video on that. Now if you're interested in making your own version of this, I'll put the design up on Thingiverse, so you can 3D print your own and do your own measurements. I'll put the link in the description. I'm so chuffed with this, it's going to be really useful in describing the difference in how a cube feels before and after I modify it in some way. I'm super excited to get on with my digital version once I've finished editing my 3 other cubing videos. So see you soon friends, give me a thumbs up, tell me what you think in the comments, and please subscribe and click that bell too so you get notified when I post a video. As you can see, I literally have 2 subscribers right now, and one is me and one is my wife. So it would be super great if you can help me out with that. Right friends, that's it for now. Happy cubing!